Yeah, so after like your last lecture, I mean, there was some interest in like the groups here, like to understand if there is like, let's say, some connection between like our ability to test better on like these augmented grid structures and some notions of mixing. It was not very transparent to me what question people were interested in, but it had like the following flavor that, we can prove hypercontractivity or like some isoperimetric bounds better for like certain augmentations. And if I get
Hmm.
better augmentation, the question that like at least one expert was wondering was the ability to test. Does it like transfer or the ability of like showing good mixing bounds? Does it like transfer to like good testing results? I was a bit unsure because mixing seems like an undirected notion, but
Right. You're saying like if you take the DAG undirected
Mhm.
and you say like, does it have good mixing properties? Is that enough to say
Yeah, some kind.
monotonicity? Yeah, I don't know. I agree. Like, yeah, it's like an undirected thing. Um, but yeah, this is something I've thought about off and on for a while. Like, through some kind of more general directed isoparametric, like, if you're partial order, if you have a DAG with some property, like, well, I guess it's kind of, mm, yeah, I don't know. Like somehow our proofs, like for the augmented hypergrid, proof of the directed Margulis inequality is like super specialized to that DAG in particular.
I see.
And but it seems like that shouldn't be the case, right? You should like you could
Well,
change it a little bit, like somehow it's actually like very specific to the edge lengths being powers of 2, and that all of them are there.
Mhm.
That's like this alternating paths type thing that Session Parnak came up with. Like that's one place where these powers of 2 are used.
I see.
And I'm not really sure if you play around with that. Like if you take these edge lengths and you like perturb them slightly, it seems like the theorem should still hold.
Oh, yeah, certainly I would hope so.
Yeah. um,
Showing that is a pain.
but yeah, it seems like there should be some more like general directed isoparametric stuff that you could prove.
Okay.
But I'm not sure. And then relate that to monotonicity testing on more general post sets or
Yeah. So anyway,
but
there was
the undirected mixing property, I'm not sure.
okay.
But yeah, sorry. Yeah.
So, like, we'll start in like 2 or 3 minutes, like just waiting for more people to join. Hello, Yadu, I see you. And Jayakumar is also here. So, hello, Jayakumar. And Rohit, I forgot to say hello to you. You're a colleague here.
Hi.
Right.
So you said it's like finals week?
This is the finals week. Yeah.
Hmm. What is like the structure of terms? Um,
So, I will defer
there.
it to like the expert here. Rohit, maybe you can like answer that question better than me. Like, this is first time I am having a finals in my class. So,
So
Rohit,
by structure, you mean which months?
Oh yeah, like we have like a quarter system or a semester system,
So we have
and
2 semesters in a year, and like one is
mm,
from August to November, and the other one is January to April.
okay, got you.
Yeah,
That's January to April. So then, um, like May through August is.
yeah, 3 months break.
I see. I see.
so you can share your screen, Hadley. All right. Yeah, that works. Let's just check that, right?
Oh yeah, let me do that.
All right.
Okay. I was going to draw a new picture, but I didn't get around to it.
It's fine. So yeah, I think we can begin. So we are very
Okay.
glad to have Hadley Black visit us again virtually. So Hadley is currently a postdoc at University of California, San Diego with Barnasaha at the Ancor Institute. He did his PhD at UCLA, where he was advised by Raghumeka. Before that, he was at UC Santa Cruz, where he did his undergraduate studies, where he was mentored by Sheshadri. So Hadley has been involved deeply in a lot of research efforts dedicated towards understanding Boolean monotonicity. And he'll be telling us about the domain reduction technique today. As you might have noticed that, Hadley has been associated with UCs for pretty much all of his academic life. I hope that trend continues. And additionally, I must thank Hadley that it's late in the night in the Bay Area and he's still here. So thank you very much, Hadley, and please take it away.
Thanks so much, Akash. Yes, hope you all are having a good morning. It's a late evening for me, so hopefully I keep up the energy once again. So today I'm going to be talking about this domain reduction technique, which comes originally from our SOTA 2020 paper. So I'll just start by reminding you of the definitions. So we're looking at the hypergrid domain, which is like the set of vectors of length d, where each entry is an integer between 1 and n. And the partial order just says x is below y if xi is at most yi for every coordinate. And of course, we can just define the notion of a monotone function with respect to this ordering. And in general, for any function, we can define its distance to being monotone as just the minimum Hamming distance between f and any monotone function. So here, Hamming distance is just like the fraction of the domain where the two functions differ. And then we can define the monotonicity testing problem. So you're given proximity parameter epsilon, then black box query access to some input function f. That's a Boolean function. And you should be able to distinguish between the case when f is monotone and when f is far from monotone. So we say when the distance to monotonicity is greater than epsilon, we say that the f is epsilon far. And in particular, it turns out that most of the literature has, at least most of the upper bounds have considered one-sided error testers, which means that when the function is monotone, you accept with probability 1. Okay. So the goal is to make as few queries to f as possible and be able to distinguish between these two cases. If the function is not monotone, but it's close to monotone, like less than epsilon, then we don't care what the tester does. And also, it turns out that most of the upper bounds obtained in this line of work are also non-adaptive, which means that all of the queries can be specified at once in one round before receiving back the value of the function on any of those points. Okay, so I'll give a quick abridged history, since last time I gave the full thing. So for hypercubes, there's been a bunch of papers which I'm not mentioning here, but they culminated in this square root d upper bound by Koopmans and Safra, and this is a non-adaptive one-sided error tester. And there's a matching lower bound by Chen, Waingarten, and G. And the lower bound is non-adaptive and two-sided. So this means that up to polylog d factors, square root d is really the answer for non-adaptive testers. You can't beat that even with two-sided error. And also, yes, I've chosen to suppress the dependencies on epsilon on this slide or in a lot of the talk actually, to kind of make things a little cleaner. So usually we like to think of epsilon as some small constant. So think of it as 1/100 or something like that. And also, yes, all of the upper bounds on this slide are non-adaptive and one-sided. So for hypergrids, so last week, but a few days ago, talked about this early paper from '99, which gave an O of D polylog D tester by sampling a random line and running a one-dimensional test on the function restricted to that line. It's an axis parallel line. And then I mentioned how a little bit of how we got d to the 5/6 polylog n in 2018. proving some directed isoparametric inequalities on something we call the augmented hypergrid, and running this path tester idea, which Session D. Parnab came up with in their 2013 paper, and which Koopmans and Safar also used to get square root D on hypercubes. And okay, so this was sort of lecture three. I talked about these. Lecture 1 and 2. And then in 2020, get d to the 5/6 without this polylog n by kind of combining the path tester result from our 2018 paper with this new technique that we call domain reduction. And that's what I'm going to talk about today. And so at the time, this d to the 5/6 was kind of incremental, I guess, but I want to stress that the domain reduction theorem is also used under the hood in our final most recent paper, which obtained this d to the half plus little o of 1 tester. So the upper bound that we obtained at the time was kind of incremental, but the theorem was kind of an important step that's used in our final result.
So Hadley, just to make sure that I remember like correctly what you told us last time, in your final result, you have no dependence on n, right? No dependence.
Correct. Yeah.
Okay. Good.
Yeah. So in this SOTA 2020 paper, d to the 5/6, no dependence on n, and then there were these two papers, right, which got square root d but poly n, and then you have to do some extra stuff to get rid of poly n. And domain reduction there doesn't really actually suffice by itself to get rid of this, as we'll see. There's some other things needed, but still this domain reduction idea is used to get our d to the half plus little o of 1. And right here, yeah, there's no dependence on n here. It's not hiding in the little o of 1 or anything like that. So, so these more recent papers, Sesh will talk about in his next two talks. Okay. All right, so this lecture is about domain reduction. Right, and so we were motivated at the time, right, by the fact that this annoying polylog n dependence. But you know, this paper from nearly 20 years before already was independent of n. Right? So this was the motivation. And so the question we asked was, can we like just reduce the case of small n, right? So is there some way to give like a black box reduction from general arbitrarily large n down to some manageable smaller n? Okay. So let's start with question. So if you were first coming to this problem of monotonicity testing over hypergrids, and all you knew was, okay, there's all this really nice stuff known about the hypercube setting of the problem, you might ask, okay, can I just reduce to the n equals 2 case? Okay. So one natural way to try to do this is take your function and, well, take your domain, right? And for every dimension I, just sample a pair of points ai, bi, just uniformly from the integers 1 through n, and then consider the Cartesian product of all of these pairs. So H, the product of all of these pairs, and this gives you like a sub hypercube within this larger hypergrid. And then I can just restrict my function to this hypercube H. And clearly, you know, f is monotone, so any restriction of it is also monotone. And now, if we have that f is epsilon far from monotone, if then the restriction is also far from monotone, then we have a reduction, right? So I just sample my random hypercube, and then if these two things are satisfied, I can now just run a hypercube tester on this restriction. So then, right, so if yes, sample H, and test FH using your favorite tester for hypercubes. And okay, so the question more concretely is, what is the expectation over H of the distance to monotonicity of F restricted to H? And is this at least, let's say, omega epsilon of F? Question mark. And so actually it's not to actually find a counterexample to this. So the answer is no. At least if you sample H in this way that I've described. Okay, so I can actually show you a counterexample. So this is, okay, let me walk through the things that are written here. So the function, the counterexample is, I'm going to look at a hypergrid where n is actually equal to d here. So this is like d to the d. And you can generalize this for any multiple of d, like n being any multiple of d, but this is the simplest way to describe the function. And the function is 1 if and only if x is equal to, sorry, if xi is equal to d minus 1 in some coordinate I. So this bold black, these bold black lines are where the function is 1. This makes sense. And okay, so the violations are kind of these red edges. Right? If I take a point where xi is d minus 1, and I increase that coordinate to d. Sorry, if I take a point with d minus 1 in some coordinate I, but every other coordinate is not d minus 1, and I increase that coordinate to d, then I get a violation. So visually, it kind of looks like it is close to monotone, but actually it's far. But first, let me back up. So why is this? Show this as a counterexample. If this function is far from monotone, we're going to show that it's like a constant far from monotone. But when I sample this random hypercube, the restriction is actually monotone with high probability. So this gives us a counterexample to this domain reduction statement for hypercubes. So how do I show the distance to monotonicity is large? So I can construct a violation matching kind of along these red edges, actually. So for every point x, sorry.
Hadley, can you hear us? Hadley's videos is frozen for me. Is it frozen for others?
Yes, yes.
I'll just message him. I'll just give him.
What happened?
Hello, Hadley. Yeah, so we had some technical issues and we could not hear you for a while. Can you hear me now? Oh, I lost you again, it seems.
Hello?
Hadley, that was me. I was the one calling you. So
Okay. Sorry, I'm not sure what happened. The like Wi-Fi flickered on and off or something. I don't know. I'm
okay.
in my office at San Diego, so it's kind of odd.
Oh damn. Okay. So let's
Maybe
try.
it's some late night Wi-Fi restart or something. I don't know.
Okay. So let's try again. I mean, you were telling us about why the restrictions to hypercubes are
Yeah.
monotone with high probability. And
Okay. Yeah.
you were earlier telling us that this guy is in fact far. So
Yes. Yes. Okay. So right. So I constructed this matching M. Now the distance to monotonicity of F is at least the fractional size of this matching. And what is the fractional size of this matching? It's just probability, like the probability that a random point, d minus 1 coordinate, and all the other coordinates are at most d minus 2. This is just I can just sum over all of the coordinates and look at what's the probability that that coordinate is d minus 1. All the others are less than d minus 2. And this is, so what is this probability here? This is just 1 over d, right? That's the probability that xi is equal to d minus 1. And then minus d to the d minus 1, right? And then I sum over all of these guys. I sum over every coordinate, and this is at least, you know, e to the minus 2 or something. So this is omega 1. Right? Okay, so this is far from monotone. But now observe that when I sample my random hypercube, the restriction is actually going to be monotone unless might have the wrong thing. That's okay. Unless AI is AI BI is equal to d minus 1 d. Unless I actually capture, right? So for like AI is here and BI is here. Otherwise, you'll get some hypercube where there's no violation. Okay, but this happens for some I with probability like 1 over d squared. Right, and so just union bounding over all I, this happens with probability at most d times. Makes sense. Right. Okay, so this is a counterexample, at least for this particular way of sampling a random hypercube, which is kind of natural. I admit that there might be some other more clever way to sample a random hypercube that might preserve the distance to monotonicity, but at least this kind of natural way of doing it doesn't. Okay, so this can't reduce to a random hypercube in this way, but we could still try to reduce to some k, where k is hopefully much less than n. So this is kind of the general domain reduction procedure. So I'll take some k that's much less than n, hopefully. And then in every coordinate I, sample a set ti by taking k independent uniform samples from 1 through n. And then look at the Cartesian product of all of these sets. And this is like a k to the d sub-hypergrid. And again, of course, the restriction to this is monotone. And now we again ask, what is the expected distance to monotonicity of the restriction to t? And can we say that it will be omega epsilon, like the original distance to monotonicity for some small k? And I'll actually note that the construction I showed you on the previous page actually shows that our construction shows that you need k to be actually omega square root d. If you look at the calculation, actually we need, in order for the restriction to not be monotone with overwhelming probability, we actually need like square root d samples. So basically k needs to be like some polynomial in d at least. Okay, so what we were able to prove that k is like d over epsilon to the 7th power, which is kind of odd, but it's, you know, d over epsilon to some constant. That's what's important. That in expectation, the distance to monotonicity is preserved. So we can get this statement. And okay, the constant in the exponent is not too important because at least at the time, right, we were just trying to turn polylog n into polylog d. So you take log d over epsilon to the 7th, it just becomes 7 log d over epsilon, and we're good, right? So this allowed us to get d to the 5/6, just polylog d. Okay. So, okay, before I talk about how we prove this, I just want to note that this kind of suggests, okay, we can turn any arbitrarily large n into something very manageable, like some poly d over epsilon. So what about, it kind of suggests that we might be able to handle like infinitely large hypergrids at a high level, right? Or even maybe like continuous domains. So, so basically, you know, define the monotonicity testing problem in basically exactly the same way over continuous domains, as long as we stipulate that the set or the function is like a measurable set. And by that, I mean like the function is a 1, a vague measurable. I'm not really here to talk to you about measure theory, but I'm definitely not an expert on that. But the definition of a measurable set is just like for any epsilon, there exists some open set E, which contains the set, and where these two sets differ on a most epsilon probability mass. So it's kind of a simple definition, and as long as you say that F is satisfies this condition, I can just define the monotonicity testing problem in exactly the same way over some continuous domain. Like for instance, I'm going to talk about like the continuous cube. So I take the unit interval from 0 to 1, and I just take the d-dimensional version of this. Okay. And now we can look at the domain reduction question in this continuous domain. Let's drink some water. So now what's happening is each of my sets Ti is formed by taking just k uniform samples from the unit interval. And then I look at the Cartesian product of all these sets, and I look at the restriction of F sub hypergrid. So now I have this continuous domain. I sample like a small hypergrid. I restrict F there, and I can again ask, is the distance to monotonicity preserved? Okay. And that actually get this continuous version of the domain reduction statement to hold by using the discrete version plus some basic measure theory. It's not too complicated. I can kind of go through the proof at a high level. So because the set is measurable, so one kind of basic consequence of a set being measurable, which you can find in like a measure theory textbook, it's almost like the definition of measurability, really. So there's nothing fancy happening. Because that I can approximate the set up to any epsilon by some finite union of boxes, right? What we can do is kind of partition, take the domain and partition it into like a grid of n to the d axis aligned boxes for some large n, right? That's kind of this blue gridding, what it represents. And that is measurable. We can argue that for any arbitrarily small delta, there exists some capital N, which depends on delta and the function itself, such that when I do this gridding, the fraction of boxes contained in the set of ones or contained in the set of zeros, so they're like on the boundary, is at most delta. So like I can get the number of boundary boxes, number of boxes on the boundary to be arbitrarily small. And now, okay, so for each z, I'll use, for each z in n to the d, I'll use bz to denote the box at that position. And now this item 2 kind of implies we can define a function f tilde, which is a function over the hypergrid n to the d. as basically f tilde of z equals f of z if the box at position z is like not a boundary box. So it's like contained, oh wait, that's not correct. If it's contained in the set of ones or in the set of, and then just define it arbitrarily otherwise. One is, okay, so this f tilde is like a function over the hypergrid that approximates f in some appropriate sense. And now when I run the continuous domain reduction procedure, it's equivalent to running the discrete domain reduction procedure on f tilde. So the continuous dr on f, the original function, is equivalent essentially to the discrete domain reduction on f tilde. And crucially, the discrete domain reduction theorem, it doesn't care how large n is, right? Right, so this n, right, like I said, it depends on delta and f. So f could be some arbitrarily crazy function, but as long as it's measurable, some hypergrid gridding that will approximate it, and then you just run domain reduction and you reduce it down to this k to the d hypergrid, where k is like poly d over epsilon. This makes some sense. Just let me know if you have any questions. So this gives us a continuous domain reduction theorem, which says for any function over a continuous domain, here I'm using the continuous cube, we can do this sampling and preserve the distance to monotonicity. And in fact, it holds for any function over, or it holds for r to the d, where the underlying measure is any product measure. So here I'm looking at the uniform measure over the continuous cube, but you can take any product measure over r to the d, and this will work. Right, so this allows us to basically port testers over hypergrids to testers over continuous domains, which is kind of nice. So at the time of this paper, this gave a d to the 5/6 tester for functions over r to the d. All right, I'm kind of zooming through actually. So please slow me down if I'm going too quick. So now I'll tell you a bit of how we prove the domain reduction theorem over the discrete domain, over the standard hypergrid. So basically the main down to doing proving that the theorem, that you can preserve the distance to monotonicity when you subsample in just one dimension. And then you'll just apply this d times once for every dimension. So we're going from n to the d to k times n to the d minus 1. Okay. So we'll start with our function. We sample this set t of k uniform samples from n, and then restrict to our new domain, which is t Cartesian product with n to the d minus 1. So you're taking this cube, you're taking this grid, and you're selecting these kind of slices, right? So each of these slices is like a d minus 1 dimensional subspace, a d minus 1 dimensional hypergrid. So these represent like the set of points x, such that the first coordinate belongs to the set t. Okay. And now what we need to show is that distance to monotonicity of this restriction is like the original distance minus some like epsilon over 2d. So then I can sum over all of the d coordinates. And then, yeah. Okay, so I'll remind you about violation matching. So this is kind of important. So again, so these violation matchings are like our combinatorial handle on the distance to monotonicity, and they're what we will use to track or to sort of ensure that the distance to monotonicity is staying preserved as we do this this subsampling. So, right, so violation matching, right, it's a set of disjoint pairs x comma y, where x is below y, f of x is 1 and f of y is 0. And okay, so for any such matching, the distance to monotonicity is at least the fractional size there. That's kind of a trivial statement if you think about it, because to make the function monotone, I have to change f on one of the two endpoints of every pair in this matching. And so the non-trivial statement is that actually there exists a matching whose fractional size is equal to the distance to monotonicity. But the point is that I'm going to use this. So by B, we have some matching to start with for f of this size. And now we're going to sampling. We want to show that after the subsampling, there's still some large matching, and therefore the distance to monotonicity is preserved. Right. So basically by A, we can lower bound the distance to monotonicity of the restriction by showing that there still is a large matching. Call it MT for F. So after you sample T, there's still a large matching, and therefore the distance to monotonicity is still large by B or by A.
Is it exactly epsilon times n to the t? Should it not be epsilon times n to the t divided by 2?
Okay, so any maximal cardinality violation matching is of size at least epsilon over 2 times n to the d, like you said. But actually for Boolean functions, you get equality here because the violation graph is bipartite.
Right. Okay.
Yeah,
Thanks.
so so like the distance to monotonicity is the size of the min vertex cover in the violation graph. And here the violation graph is bipartite, so the maximum matching is actually equal. You don't lose the factor. Okay, yeah.
Okay, thanks.
Yeah. Okay. So it's always nice to kind of start with the d equals 1 case. And in this case, this will actually help us with the full d-dimensional version. So what is the d equals 1 case? So we have some function on the line, and I have some red matching to start with. And I'm going to sample some k coordinates along this line. This set is t. And right, so I sample some coordinates here. Trying to copy what I did in my notes, which is sort of tedious. Right, so you sample these blue things, and we restrict to just this subset. And now we want to say that look at the points that were matched by the red matching, and we try to find some new matching amongst those points. Right. So for instance, I can match now this guy to this guy, and this guy to this guy. Makes sense? And we want to say that the matching like the fractional size of the green matching is close to the same as the fractional size of the red matching. That's what we want ideally. Or in other words, the size of MT, roughly like K over N times the size of M. So note that, right, for some point in the domain, probability that this is selected by T is like K over N. Okay, so this is what it would be if you were sampling without replacement. We're sampling with replacement, but let's imagine that K is so much smaller than N. Never get a collision, right? You're never going to sample the same thing. So like the probability of that happening is negligible. So this is like equivalent to sampling without replacement. Right. Okay. So some small technical details. So yeah, so we'll say that, the probability of sampling any particular thing is like K over N. And so, okay, I could try to preserve the pairs exactly, but the probability that I actually get both those points in T is like K over N squared then, right? But that's bad, right? Because we want to actually get like K over N, not K over N squared would be much too big of a loss. But we can observe that we can do much better, right? We don't have to preserve each pair exactly, right? Because for any, so I've ordered these pairs according to their lower endpoint, like we did for the line tester analysis. So if I take any I at most j, xi match yj, right? If I select xi in T and I select yj, I can actually match them in the green matching, right? For any I less than j. And so this observation, right, we're exploiting the total order on the line, and this allows us to prove a stronger bound on the size of the green matching. So actually, this was studied previously by Berman, Raskadnikova, and Yaroslavstev in a paper in 2014. They had a bunch of other results, but in here was kind of this domain reduction statement for one dimension. So they said that in expectation, the fractional size of the green matching is at least the fractional size of the original matching minus this quantity that is decaying with K. Importantly, yeah, this is, as I increase K, this is actually going to 0, right? In particular, I can set K to be like 1 over epsilon squared, right? And I will preserve the distance monotonicity. Or, yeah, no, 1 over epsilon, sorry. 1 over epsilon. So, so in particular, like for our purposes, we want this loss term to be like epsilon over d, right? So here I could set K to be like squared over epsilon. And we would get that the expectation of the distance to monotonicity of the restriction is at least epsilon minus epsilon over d. So, okay, this is kind of giving what we want, but we need to get it to work in higher dimensions. Make sense? Are there any questions? Okay. Okay, so what happens in higher dimensions? So actually, let me take a sip of water here. Okay, so now we have our function f over the d-dimensional grid. and we're sampling the set T. And now T is like taking a full D-1 dimensional slice of the hypergrid, or taking K of them. And again, we have this red matching for F, and now we want to construct this green matching for F after the subsampling. And now what we want is like the size of MT. Again, we want like the fractional to match. Now the size of the domain is like K times n to the D-1. So we want this to be like M over n to the D. Like we want these to match up. Okay, so what we try to do is try to average over every line in some sense and apply the D-1 dimensional argument. So for a line L, remember a line I'll think of as just restricting the coordinates 2 through D to some value Z. And I'm letting the first coordinate be free. So it's like a one-dimensional subspace. And I could take my red matching and look at the pairs in this matching where the lower endpoint X is on this line. Right? So that's like, kind of looks like this. This makes sense. But note that the upper endpoint, like M is just a matching an n to the D, right? So this upper endpoint Y, I have no guarantee of where it is. Right? It might not actually be on the line L. It could be, you know, off some other place. Right? Does that make sense? Okay. And okay, so let a little bit of notation. Sorry for all the notation, but I think I need it in this case. So let me let ZLT be the points Z matched by ML such that Z1 is in T. So look at all of these pairs matched by ML, and then I subsample, and then I look at the remaining points that belong to that matching. Sorry, I look at the points belonging to that matching that are still present after the subsampling. And we want to say that we still find a large matching amongst these points. We can find this green matching MLT amongst these points, whose size is like fractionally the same as the original red matching on L. So maybe it's better to write.
Hadley, what's ZLT again? So ZLT definition, you are saying points Z that are matched by ML such that Z1 belongs to T? Is that Z1?
Yes.
Oh, all right. I see. The first coordinate. Okay, fine. Sure. I see now. Yeah.
Yeah, like the points that are still in the domain.
Good. Yeah.
The reduction. Yeah. And we're trying to find some green matching amongst these points that survived.
So
Okay,
Z1
so
is
this
one among the K things that you said.
Yeah, correct.
Sorry.
Exactly. Yeah, perfect. Yeah. Okay, so we try to do the same trick, like in one dimension, like we did in one dimension, right? I'll take ML and write down like an ordering on these pairs, right? According to the position of the first, the lower endpoint, right? And I can observe again that for every I at most J, you know, Xi is at most Yi. These 2 points survive, I can match them in the green matching. Right. Okay, so now, hold on 1 second. I have something on. I'll write this down. So if, you know, if Xi1, Yj1 are in T, then can match them in the green matching. So then the question is, can we just apply the d=1 lemma?
So just a question. Are there
Yeah.
matches which can be restricted to within a plane, like going vertically up?
Yeah.
Okay.
Yes. So yeah, like x1 could be matched like this. Is that what you're asking?
Yeah, and that doesn't exactly fit into the one-dimensional framework, or does it?
Yeah, precisely. So yeah, so everything yeah, this observation is still true. But yes, so I was gonna ask, like, does anybody see the problem? So you already see the problem, which is perfect. So I was gonna say, like, you know, we can kind of projecting all of these points down to L and then just applying the one-dimensional lemma. But the problem is, yeah, we have no guarantee that these points are all in different slices. And really the big problem is that the y's could all belong to the same slice. So we could have like this picture. So all of these upper endpoints are lying in the same slice. And now this is a big problem because, okay, what is the expected size of this green matching now? Now, if I don't select this one slice, I get nothing, right? So now, you know, the expected size of this matching is like the probability that, so if this slice is like corresponding to value A, so yeah, A is like a value in 1 through n, and all of the y's belong into slice A. So the expected size of this green matching is like the probability that A sampled in T, and then conditioned on this, it's like the expected number of x's that we get. So it's like the expected number of xi such that xi1 is in T. Right, but this probability is k over n. And this expectation is also k over n times the size of m. So we would get, in this case, we would get k over n squared times m, which is very bad again. This makes sense? Yeah. So yeah, this is bad. Okay, so how do we avoid this? So this brings us to like the crux of the problem, which is this idea of stacks, kind of just a word that we decided to assign to this concept. I don't know if it's a great word for it, but we call this a stack. So for a line L, a slice S, here again, L is a one-dimensional subspace, and S is a d-1 dimensional subspace. And the stack corresponding to L and S is the set of pairs in the matching where the lower endpoint X is on the line L, and the upper endpoint is in the slice S. Right. And now, right, so the problem that arose was we could have a stack that's really large, and that's a problem. Right, so this is the picture. But so we're able to show, right, if say that stack is bounded by some lambda, then basically we can get the one-dimensional statement to go through. Dimensional argument goes through with some loss that depends on lambda. Does that make sense? Kind of intuitively, like the one-dimensional argument kind of applies here, except, you know, when a lot of things are in the same slice, you get some problem, right? So if we can just say, you know, not too many things are belonging to the same slice, then kind of the same thing should go through. Does it make sense? Okay. Okay, so if we can see that there is some matching M where this lambda, so where, you know, every stack is bounded by lambda, where lambda is like poly d1 over epsilon, then we get what we want, right? Because, you know, if let's say instead of lambda here, I have like d to the 7th, right? Then I can still set k to be some polynomial in D and get this term to vanish. Does it make sense? Okay, so this is like the crux of the whole paper, which is that there always exists some m where the stacks are not too large. So I'm not going to show anything about the proof of that. It's like super, I don't know, it's very like technical and kind of funky. But it'll just show some example. Like, so let's look at this function where the diagonal you have ones and above the diagonal you have zeros. So the matching on the left has large stacks, right? If you look at the L along the line along the bottom and the slice on the far right, you have a stack of size 4, right? Like all of these points are matched to these points. So this is like a bad matching. But you could rearrange things and get a completely different matching, the blue matching, where all of the stacks are of size 1. So I've rematched things, right? So now for every L and every S, the number of pairs that go from L to S is 1, at most 1. Right, so now here, the only pair going from L to S is this guy, for instance. So okay, you kind of spread things out. Right. So in general, we were able to show that like the stack size bound informal statement. There always exists a matching M, like a maximal, that's important, or a maximum cardinality violation matching M such that the size of every stack is at most poly d 1 over epsilon for almost all, actually not every stack, but for almost all LS. So this is like the part of the paper that we were stuck on for a while. Most of the other stuff kind of fits together nicely, but then this was very tricky to figure out.
But I would imagine that like this good matching, like with respect to which, like, you know, these matching size, the stack size is small. So like this is something that your algorithm should not care about, right? I mean, this is something only in your analysis. Yes.
Yes. Yeah.
Okay.
This is all just to prove domain reduction, right?
Yeah. Yes.
And we're trying to show, you know, you have some matching and then you sample and then you still have a large matching. And it seemed very like natural and nice to try to do this thing where you average over all the lines, right? So you take your matching, you look at some line, and then you take the pairs in the matching that kind of where the lower endpoint is on that line, right? Yeah, so it's just kind of the approach that seemed the most manageable, to go by averaging over all of the lines, and to get that to work, you have to like find some matching where
I see. So
this happens. So maybe you don't.
So I think what
I don't know.
Was does this for almost all stacks suffice? And indeed it suffices. Like the way you are going to like subtract out the loss will be even if like this works for most of the stats, right?
Right. Yeah, correct. Wait, sorry. You
I'm sorry.
sorry. What was your question? Sorry. Sorry. Can you say your question?
Yeah. So like I guess I was trying to understand if like I should still be happy when I have this version, the version that you wrote, which works for almost all stacks. Like there are some stacks with respect to which I could be bad, but I guess
Yeah, exactly.
still fine because I will not incur too much loss.
Yeah, exactly. Kind of like if uh, like a 1 over poly d. I can't remember exactly the statement, but yeah, if you get almost all, up to some error, which I'm forgetting, then yeah, you can just take that loss and you're fine. Yeah.
Okay. Thank you.
Yeah. No problem.
So just to recap, proving that most of the stacks are small, it tells you that your MLT size is necessary, right?
Right. So it allows us to apply this lemma.
Right.
So yeah, we
So
want
if MLT is large, then then your tester will sample a violation with hypergrid.
right. So if MLT
Is that what it is?
MLT. Let me back up. So this lemma says, okay, we can get this statement to hold for some reasonably small lambda. Now that means that this inequality holds for k
MLT
being
is
like
large.
poly d over epsilon.
Right.
So now this means that backing up now. So that means that for every line, so I can take my matching. I look at the subset of that matching where the lower endpoint is on L.
Yeah.
And after I can show that after subsampling, I still have this. I have this green matching MLT, which is fractionally like the
large.
same size as the original one. Then now I take the union of all of those.
Yeah.
That gives me this matching MT,
Mm-hmm.
which is large enough to say that the distance to monotonicity of F of this restriction, that this guy is far from monotone.
Yeah.
And that proves the main lemma. Yeah.
Right.
Does that make sense?
Yeah, it does.
Good to go in reverse. Okay. So yeah, that's the proof. So in summary, right, it suffices to do this reduction for one dimension and show that you get a loss of like epsilon over 2d. For k being polynomial d in 1 over epsilon. And the proof is like we average over every line. And we can apply the d equals 1 argument as long as these stacks are not too large. And so the crux is then finding this matching with small stacks. Okay, so some concluding remarks. Right, so the whole point of domain reduction is to get this black box reduction of monotonicity testing over n to the d down to k to the d for Boolean functions. So again, we can now sample a sub-hypergrid of size k to the d and just test whether the restriction is monotone. And this works even for continuous domains, which is nice. And like I said, this technique, action theorem, is actually used under the hood in our final result. So I think it is kind of like an important part of all of this. It wasn't just like an incremental thing. What else did I want to say? And actually, yeah, so speaking of this continuous thing, so this final result actually also holds for continuous domains as well, due to this continuous domain reduction. And I'll also mention that Harms and Yoshida, they had a paper in iCalc 22, which gave like an alternative way of reducing the domain. And it's slightly more efficient. They actually get reduction to d over epsilon cubed instead of d over epsilon to the 7th. But their method is not really black box in the same way. Like they don't prove the same statement that you sample a random subgrid and the distance to monotonicity is preserved. But it is like a domain reduction style result, which does reduce the problem to testing over a smaller domain. So I just want to give them
So just double
give
checking.
them a shout out.
So just double
Sorry.
checking. If I want to like take the benefit of like their analysis, the analysis by Harms and Yoshida, do I have to start using adaptive testers? If I want to leverage.
I don't think so. I think their tester is still non-adaptive.
Okay.
But it is like a two, they kind of like combine two tests. Okay, I don't remember exactly how it works, but I think it is still non-adaptive.
Okay, great. Yeah.
And it is a bit like conceptually simpler, but like their proof is a bit simpler, but I still think I like our statement, right? We prove like, actually you take a random hypergrid, a random subgrid, and the distance to monotonicity is preserved. So I think that's why I chose to present this, because I think the statement is kind of nice. Okay.
So by saying that the method is not black box for domain reduction, yeah, does that mean that you have to spend some queries and doing the domain reduction itself? That is part of the query complexity of the tester? Oh, that would make it adaptive. What is that?
No, so I think what they do is take the domain and partition it into some small boxes, kind of like we did for continuous. And then test, like run the monotonicity tester. Hold on. It's like they run two kinds of tests. One is basically if almost all of the boxes are on the boundary of the function, then I think like running just any like monotonicity tester on like the F tilde that you get will work. But then they run some other tests to see if too many of the boxes are lying on the boundary. And if you have too many boundary boxes, then basically you know that the function is not monotone to begin with.
Nice.
So they run like two different non-adaptive testers.
Right.
And if one of them fails, then you know the function's far from monotone. But if it succeeds, then the domain reduction worked, basically. Does that make sense?
Yeah, this is good enough.
I hope they don't watch this, because maybe I might have butchered the explanation, but I think that's basically what it is. So.
Yeah, in the continuous to discrete reduction. So does it make sense to say that F tilde is delta far from F?
Let's see.
Is that incorrect?
Yes, I think so. So let's see. Right, so a delta fraction of the boxes. Yeah, I think that is
Okay.
close. Like it can differ only on the boxes that are on the boundary.
Yeah.
That will constitute like at most a delta fraction of the domain.
Correct.
Yeah. So yeah, exactly.
Nice.
Okay. Yeah. So So yeah, so the next two lectures will be by Sesh. And yeah, I think you should really look forward to those. He's like a really good speaker. And yeah, in the next lecture, I think he'll talk about our stock paper where we generalized this directed Talleyrand inequality for hypergrids. So this was originally proven by Koopmans and Safra, and we were able to generalize it to hypergrids. And then in lecture 6, he'll talk about this final d to the half plus little o of 1 result. So yeah, that is all I wanted to say. So yeah, thank you so much for coming, and thanks for your attention. I appreciate it.
Thank you, Hadley. Thanks very much for the great talk. And
Thanks.
yeah, late in the night for you. And thanks still for like taking a time and like staying up for us. And yeah.
Oh yeah, of course. I somehow I was able to keep my energy up much better this time than last time. I don't know why, but
Good times
yeah,
were great. So
it was
yeah.
fun.
So looking forward like to the next talks by Seshadri, and like thank you very much. Thanks for the beautiful talk.
Yeah, absolutely. Thank you so much for having
Thank
us
you,
and
Hadley.
for organizing this. It's great.
Bye.
All right, thanks a lot. See you.